So, hi, I'm Will. Amongst other things, I started a company called Spiral, but today we're talking about actually open source project called Vortex, which I'm also the sort of TSC or PMC chair of. So I'm going to talk about building GPU native columnar storage. A little bit about me. Well, I've dabbled in lots of stuff. I guess kind of like what you would call AI research really long ago. I was a derivatives quant. The big thing is actually this is not my first exabyte scale data system. I sort of helped create Foundry and scale it at Palantir, and that was sort of like did basically everything that read or wrote bytes while I was there. Um, I like to back up a little bit, which is like, let's start at the bare metal, because I think everything in data systems is actually a bit downstream of hardware. So if you go to sort of, the early 2010s, or even go further back, like 2000s, it's like individual CPU cores stopped getting faster. And so Moore's law sort of happened by scaling out lots of CPUs. And the 2010s were all about like have this big homogeneous pool of CPUs and RAM, and oftentimes spinning hard drive disks, and you network them together. And there was a speed hierarchy of like RAM is always faster than disk, which is faster than network. I think the stuff that's happening now is like a lot of those assumptions are sort of no longer valid because of shifts in the hardware. Like the most obvious thing is AI workloads have really driven the explosion of accelerators, especially like GPUs, and sort of GPU compute, I think, is here to stay. Just as a percentage of wafers of silicon being produced, it's going to keep going up. And then I think that speed hierarchy still holds for latency, but there are sort of different things where network cards now have more bandwidth than the PCIe bus. So like you can actually copy more data over a network card to a GPU than you can from RAM on the same machine, or from NVMe, like local disk, on the same machine. And then I think storage has really bifurcated. Spinning disks are no longer really directly used in the same way, except as a backend for object storage. And then, there's sort of this remote infinite storage that usually looks like an object store. And then there's NVMe, which is local and extremely fast and is almost an extension of memory. I think of database systems like we had sort of the original human scale data in, human scale data out. That was from the pre-2006 era of Dennard scaling, when CPU cores just got faster, but there was only one of them on a machine. It's like Postgres is archetypal of this thing. And then there's sort of big data that was downstream of like, we're going to scale out CPUs. But that was all about aggregating. It was like, cool, a human is still going to consume it as a dashboard or a chart. So even the lake house, it's like, cool, you collect enormous amounts of data and then produce something very small for a human to look at. And I think we're now in this like sort of data systems have to deal with machine consumers. So enormous outputs, whether it's a single output set or huge QPS. Like I even think of GitHub falling over as like, well, it turns out that when you have these sort of autonomous agents running workloads against a data system, like it scales and breaks in like sort of new and interesting ways. And then obviously there's like this heterogeneous hardware, so stuff like training. I think the other thing, just to contextualize, there's been a big move towards composability. So Apache Arrow gave a framework for sharing in memory across frameworks and across languages, and also for inter-process communication. The Arrow file format is effectively uncompressed, so it's not ideal for at least certainly all storage use cases. Like you can use it sometimes, but it's not ideal. And then there was a big move towards table formats, Iceberg, Hoodie, Delta being the most prominent, but there are also others, and Parquet, because I think as a complement to the in-memory sharing that Arrow gave you, you had sort of like, I can share files in S3, and that's effectively, it's a near infinite bandwidth way to share between systems. Like these are two different ways of sharing data between systems. And they're quite complementary. And Iceberg and other table formats sort of wrap up the metadata around files, like usually Parquet, so they could be a table. But file formats like Parquet define how the bytes are actually stored. I usually think like looking at all these shifts in hardware, it's like, is Parquet good enough? And this is a debate I have quite often with different people, and reasonable people disagree. But I think, the things about it are it's widely supported, it's mature, it has good community governance. And Julian Ledem likes to say that Parquet is the consensus mechanism more than it is the technical implementation. As Hannes Melissen says, the format is great. Of course, Hannes is comparing it to CSV. I think the problem is it's borderline impossible to evolve. Like if you look at the default Iceberg writers now in Spark in the year of our Lord 2026, they're still writing Parquet v1. Like the Parquet v2 feature set of like optional extensions is like basically 10 years old and still not the default. Adding variant has been Herculean. It's optimized for sequential access. Like it was quite reasonable, again, for building in HDFS against like local hard disks, but it's not great for object storage. Like especially the metadata is sort of not ideal when you have to do multiple like long network requests to get parts of a file. And then the heavyweight block compression is CPU hungry and it's slow. For context, why do I care about this? I put myself in building a data system for machine consumers. And so especially for GPUs, I think about like a lot of what I think about is GPU data loading and sort of data warehousing and like, optimizing for throughput. Analytics, lookups, but like, again, especially like some of these like GPU native workloads are pretty weird. But as I said, sharing files in S3 is an infinite bandwidth way to share between systems. I think in general, if you want to maximize throughput, the most practical way is to stream bytes straight from object storage over the network, because as I said, the network cards have more bandwidth than any of the local resources on like a lot of modern servers. And then, Parquet, for better or for worse, is like the prevailing standard that defines how bytes are stored. And so if you're sending it straight over the network, especially straight from storage, you're going to get bytes defined by the file format. This is why we created Vortex. It's next-gen, composable, free and open source forever. It's Apache 2 licensed, but more importantly, we donated it to the Linux Foundation, so it has sort of neutral multi-party governance. We can't rug pull the license. I like this quote from Wes McKinney, who's actually a member of the sort of project management committee, which is, we tried to take the cutting edge in research combine it with industrial scale engineering, and then like actually for this sort of composable data systems era, it's like, can we make something that sort of actually like is composable data system, like Arrow native for this like next gen of computing. And in general, the thesis of the project was technically advanced organizations just keep building Parquet alternatives because Parquet is too slow. And bleeding edge open source projects don't use Parquet by default because it's too slow. So could we obviate the need for all these proprietary file formats with an open source alternative? Vortex basically extensible and future proof, special emphasis on sort of the GPU computing, and we'll talk about why that's important, but also just in general, like how do we avoid calcification? So as much as we can, sharing an implementation rather than having a huge, and language bindings rather than having many other ones. We wanted Pareto optimal performance. So there's a thing here, which is like, what is the most extreme performance upside that we can get? Because file formats actually tend to be quite high inertia and last for a long time. And so we wanted to push that early. So I think, scanning decompression on a CPU, it can be 15 to 20x faster. On a GPU, up to 100 times faster. Like talking terabytes per second of decompression throughput. And then can you do fast random access while preserving compression? So like, can you be comparable size? And then again, can we also get faster write throughput, especially on a CPU? And then finally, maximally error native interoperability. Design goal, actually the biggest thing was moving stuff from the spec writer to the file writer. So it allows for more evolution over time, optimizing the metadata. And then the thing we're really talking about today is, I think one of our key insights in the project was if you design for GPUs, like SIMT programming, actually has the tightest constraints. Like if you design for SIMT programming, you can't have data dependencies. And you also need to know the output size. If you don't have data dependencies, it's a lot easier to do vectorization, so SIMD. And then also to support random access, as in like maybe decompress just a single value, or don't have to decompress like large blocks, megabytes of data to get a single value. And so we pair that with cascaded lightweight encodings to get a good compression ratio. So, we pulled lots of the state-of-the-art research. It's also one of the things I'm really proud of is Vortex is starting to be used in more research, including the best paper last year. And then I think it sits at this interesting space in the ecosystem where it's sort of like cutting edge industrial strength and has sort of proper open source foundation, big foundation governance. It's like the intersection of all these. Going back to, sort of what we ended up with, if you look at Vortex, the file format, it's actually designed to be extremely extensible. We're not going to go into the per byte layout of the file format today. We don't have time. But, encodings, the compressor, which is sort of the encoding selection strategy, expressions on encodings, the data types, the layouts. So literally, do you have row groups? Do you have packs? Do you have all column written one at a time? Like how those are, the sort of byte buffers are laid out in the file are all extension points. And the files themselves are self-describing, which moves decisions about if you want row groups or not, for example, from the spec writer to the file writer. And then, having a shared implementation from an engineering point of view purely means that you can ship features to all the languages and all the frameworks simultaneously and immediately, instead of having to implement it once in one and then go through the long exercise of implementing it in all the others. So a way to think about it is that Vortex is in some ways like an LLVM for file formats. It provides an IR, has extreme extensibility with batteries included defaults. In this sense, I think we took a lot of inspiration from Apache Data Fusion. And then there's an aggressive move towards sort of the spec is so flexible to give us sort of future proofing for new workloads in the future. The other big thing, as I mentioned a minute ago, is this processor portable performance. So no data dependencies gives us all of these things. It gives us fast random access, SIMD friendly on vectorization on a CPU, and SIMT friendly on a GPU. And then the trick after that is, can you still get the file size to be small? Can you get good compression while sort of preserving that, which means actually applying all those constraints and not relaxing those constraints? And so the cascaded lightweight encodings, a lot of that has been pulled from, as I said, sort of state-of-the-art research, plus some research that we've done ourselves. And then, the key idea was that designing for the tightest constraint, which is GPUs, gave us all the other ones essentially for free. The other thing is, we in Vortex, another way to think about Vortex actually is, because the file format, there's real work there, and it's so extensible and so meant to be so flexible and so future-proof that actually, if you look at the code by lines of code, the majority of the Vortex library is actually an extensible state-of-the-art compressor for arrow data, and also a framework for late materialization, which is another way of saying sort of compute on compressed data. My example for late materialization, and this here is what I call sort of expression pushdown, is if I've compressed a column and say I know that column is constant, it's a constant value like 42, and then I want the sum of that column, I can just turn that into multiplication. And so there's lots of stuff you can do actually taking advantage of these lightweight encodings. It opens up a huge number of optimizations. So the Vortex library actually tries to ship as many of those optimizations as possible and across different notions of compute. So, we can actually ship backends for a bunch of these across, for example, NVIDIA GPUs, like a CUDA implementation, as well as sort of vectorized ones for CPUs and future backends. And so you can actually hook this into a query engine and get support across different sort of, it's like native support for GPUs or whatever it may be. But more importantly, again, the file format, I actually think a lot of these optimizations are file format specific. They're not engine specific. And so at least the ones that are file format specific are worth implementing in the file format library once optimally, instead of implementing it n times in the engines. And so that lets us then add a new support in a new engine and get immediately phenomenal performance without too much work. Going back to sort of examples of extensibility, for those of you who follow the space, Turboquant made a big splash about a month ago. crashed memory stocks briefly. We actually merged it as a Vortex extension about a week later. The cool thing about Turboquant is actually it's a serialized scalar function for rotation, and then we have some stuff on the tensor data type, and then but it basically was a strategy rather than a full encoding. And so you can get, for things that support it, you can get state-of-the-art, near lossless quantized vector embeddings stored in stuff like iceberg tables with Vortex, and you don't need a vector database, you don't need another table format. That's actually, I think, a file format concern around how do you compress and push down data on things like embeddings. Places where Vortex is out in the wild, there's a bunch of ongoing work. I gave a talk at Iceberg Summit a couple weeks ago around there's a proposal to add Vortex to Iceberg. I'm very hopeful that happens because I think it would actually be good for the ecosystem and the project. As I said, it was used in the AnyBlocks paper, which won best paper at BLDB last year. Turns out, I summarize this paper as the best way to make Parquet fast is to embed a WASM build of Vortex in Parquet. And if you do that, then all of a sudden Parquet is fast. This was pretty cool, like Liquid Cache by Shangpeng Hao over at Wisconsin. He found actually that having it cached in memory would still sometimes be slower than just reading Vortex from disk or from S3, which was kind of crazy. There's some recent work on Iceberg indexes related to the Iceberg work. It turns out if you have Vortex and you want to filter to primary key indexes, this is an example of a very selective sort of SQL query. Doing it in Parquet for one key was 116 milliseconds. Vortex was about 1 millisecond. For 90 keys, Parquet was 135 and Vortex was 6. This was someone else ran this and just posted it in our channel a week or two ago. For stuff like data loading, we plugged it into Mosaic data streaming, which has its own custom row-oriented format, and out of the box with no tuning, Vortex was about 2x faster in terms of GPU throughput. And this was months ago. Actually, I think it's probably better now that we have native GPU scans. Polar Signals is an observability startup. They forked Delta Lake and replaced the Parquet data files with Vortex and the JSON Delta log with Vortex, and it dropped query times by about 70%, which is pretty cool. Benchmarks we've done. So the GPU scans, like I said, if this is for mostly numeric data, but Parquet reading, this is actually in-memory Parquet on a GPU, in-memory Vortex on a GPU. Parquet would get 90 gigabytes a second on a B200, and Vortex gets 5.7 terabytes a second with kind of comparable roughly 5x compression ratios. And so it's like quite a bit, something like 60x faster. For direct, this is a little more subtle. So this is reading from a single disk to GPU. So this is on a modern NVMe with 8 gigabytes a second of bandwidth. And so the compression ratio for both Parquet and Vortex was about 4x. And scanning it from the NVMe onto an H100, we're measuring throughput of uncompressed data on the GPU, and Vortex got basically 32 gigabytes a second, which was, we fully saturated the disk. And you just cannot do better than this from a compression ratio point of view. For random access, I think in general, this one's a little out of date. Vortex and Lance are probably roughly in the space the fastest for random access. They tend to be pretty comparable, which is to say hundreds of times faster than Parquet. For compression, writes are about 2.5 times faster. Scans, that's full decompression on our benchmark set, is 18 times faster. And it's about the same size. So sometimes it's half the size of Parquet, sometimes it's 50% larger. It's data dependent. I think on average, it's maybe 10% larger. For analytics, this is my favorite. So it turns out that the fastest file format for running ClickBench with DuckDB is not DuckDB native. It is Vortex, which is kind of fun by like a pretty wide margin. For normal sort of analytics queries against various backends, Vortex generally wins across query engines. Same against local NVMe. This is from my Iceberg talk a couple weeks ago. So plugging Vortex into a Spark Iceberg Vortex workload reduced query time pretty significantly. So dropped I mean, Spark is harder from a percentage sense to optimize because it has so much overhead. Again, for selective filters, you see like we end up to being somewhere between 2 and often 4, sometimes much more faster. So the more selective the filter is, the faster Vortex is as a multiple of the Parquet performance. And this is my short summary. It's like basically, if anyone doesn't remember, this was before Kanye was canceled, but from his 2005 Grammy speech, like my general summary of performances for Vortex, like it's Pareto optimal. So we kind of cover all the bases. You want to learn more? This is a quick overview. I gave a long talk to CMUDB back in the fall that's updated to up to date enough. It's an hour long, and I go into like really, really in the weeds on like byte by byte the file format and encodings. And in general, if you're interested in the space, love to collaborate both in research and in open source. Whether it's already used in a bunch of open source projects like Milvus, Paymon, as I mentioned, trying to get into Iceberg, and then doing a lot of work with researchers. It's in DuckDB, we test for data fusion, but it's like in general, how do we build on this and collaborate on making it better? Cool. Q&A.
All right. So while people are getting their questions out and ready, I think now would be a good time to revisit this poll and see where we're at. And also, by the way, on that talk, dude, I'm just blown away by how fast those benchmarks are and everything that you showed. Good Lord.
Yeah, I'm very proud of the benchmarks, but it's also, we spent like 3 years really, really, really deep on this one thing.
Yeah.
Just like
Yeah.
how do
Better be.
you design the optimal file format, a columnar file format?
Huh. Yeah. What was the impotence for this? What was like the pain that you were like, oh my God, I can't live with this anymore. I need to go and spend 3 years of my life dedicated to
Um,
making a file format.
it was in general. I mean, I actually rolled Parquet out at Palantir in 2014, and had spent enough years building lakehouse shaped systems to get the sense that like it was a problem that everyone was avoiding, but it was holding back the types of data systems that you could build. And then especially over the last few years, it just became clear to me that like the types of data systems that need to be built are very different than the ones we built before. And
Yeah.
so you have to change the constraint.
Yeah. So
Ooh,
we've
what's the
got,
drawback?
yeah, that's the question. It was all freaking rainbows and roses in your
Yeah.
talk, but I'm sure there's
Um,
something.
I'd say the main drawbacks are like breadth. The biggest one is breadth of support. It's like cool. We have bindings in Python and in C++ and in Java and obviously in Rust and a handful of other sort of languages and frameworks. Parquet and others, existing things just have been around longer and have like ambient, deep support everywhere. So your framework may not support it yet. I'd say the other one is the Rust project. If you use it, is like the file format is quite stable. It has extremely good backcompat and extremely good performance. The API like breaks all the time if you link against the sort of Rust library directly. But I think
That's the,
those are mostly project maturity things that should get better and better over time. It just takes time.
yeah. Well, shoot, man, I just looked at the time. I gotta get you off of this stage and keep us. I'm already over, and I had one job. That was it. Will, thank you.